Good evening, YouTubers. Today we're going to be discussing a little bit about energy balance. We're going to be doing an energy balance for a tank. That's right here, the tank that has, for example, an inlet and an outlet, so that we can say that there's a flow of material continuously into the vessel and there's an output. As you can see, I only put in the valve, the control valve, right at the front. All right, so that implies that whatever is M1, the flow of material in, let's say that the unit here are going to be kilograms per second. So this one here, which will be M2, because this is line 1 and this is line 2. So basically what we're going to have is that M2 dot is equal M1. Right? So that's the way it is. The vessel is full. So that means that the chain of mass, total mass within the vessel never change. That means that the MDT equals 0. So the mass is constant. At the end here, what we are saying is that the mass inside the vessel is constant. Alright, so now how we do the energy balance? Let's say that this tank, let's think about it, and let's say that it's adiabatic. So there's no exchange of heat with environment, so it has a cover that will avoid the exchange of heat. There's no heat exchange, so that means that this vessel is adiabatic. Alright, adiabatic. Now, with that said, like, the question is, let's say that it has an element, a heating element that can irradiate heat, and let's say, for the sake of the argument, that it's kind of a well mixed somehow. All right, either has a mixer or there's something that can allow this to mix a little bit. So that will make that the temperature here at the exit, which is typically T2, that's the temperature also inside here, T2. Now, this heating element, let's say that has something that you can change the voltage, and therefore you can change the watts that this will produce, and let's call that a variable voltage regulator, or a VVR, and this obviously connect to a plug for electricity, and you only have to change this either from 0 to 100% full power. Now, what's the story here? Let's say this, what is going to happen is that this VVR will control the amount of heat that you get inside this vessel, which is called QR. Now, how I plan to do process control on this vessel? Well, for one, I'm gonna have, let's say that I have a TI, put it here, TI, a sensor that measures the temperature inside the vessel, but I have also a controller, a TIC. Now, this TIC can either control the flow valve or you can control the VVR. For this practice, let's say that the controller output will go to the VVR. So you set a set point. The variable that we're gonna be manipulating is the QR, because this affect QR. So therefore you can have, like, for example, a QR max, let's say for this vessel, which is basically a tank that you can find in your home, like for heating water. So let's say that is 5 kilowatts, and that's QR max. Now, depending on where you set the CO for that variable, let's call that COR, which is the one that control the variable voltage regulator, then you can have either from 0 value on QR to a maximum of 5 kilowatt. The same happen here also with the amount of mass getting into the vessel. That amount of mass, I can write it here, and let's say that M1 maximum is about, let's put a number here, 0.126, and that would be kilograms per second. So that's the basically, if you make the math a little bit, this is about 2 gallons per minute typically at a home. That's the flow, the amount of in a volumetric flow, that would be 2 gallons per minute. In mass flow, which is for this energy balance, is better to have it in kilograms per second. So now here we have material getting into the vessel, but materials get out of the vessel, but also we have heat getting into the vessel. So how we do this energy balance? Well, that energy balance will be whatever is getting in. Let's write that down. Let's say that's going to be M1 times the calorific capacity of the fluid times the temperature in. Let's call this the temperature in T1, and minus some T reference. That's we're gonna do. That's for energy getting into the material. Now that T reference, you will see in a second that it will disappear, but this is typically how you write energy getting into the tank. That's positive. We multiply this by delta T, which is for some amount of time that we are analyzing this case, minus, I'm gonna use the same M because M2 and M1 is the same, so that's why I don't have any. Actually, let's write it here just in case. M1, this is gonna be M1 as well, because it's M2 is equal M1. Now times Cp is the same material. I mean, remember, this energy balance is done in a fluid, or what we call a single phase. It's not changing the phase, it's still on the liquid phase, times T2 minus T reference. All right, now here we have material getting in, energy getting in, energy getting out, and this has to be multiplied by delta T. And now we have also heat getting into the vessel by QR, so that means plus QR, and that has to be multiplied by delta T. So this is positive, this is positive, this is this is positive, negative, and positive energy getting in. That has to be to the change of energy inside the vessel, so that would be M Cp T plus delta T. Notice that M is a constant, Cp is a constant, only T change with time. So here it's going to be mCp temperature evaluated at T. If we divide this by delta T, both sides, then this cancel out here, this cancel out, and this gone with this one, so end up being M1 Cp T1 minus T reference plus minus M1 Cp T2 minus T reference plus QR equal. Now here we go. This is the definition when we do this in the limit that delta T approach 0, then this is the definition of a first derivative. So it's as easy to say that this is like this, mCp T, and that's what you have. Now some simplification here. Let's work some simplification here. You can see that I have M1 Cp T1 minus M1 Cp T reference minus N1 Cp T2 minus N1 Cp T reference plus QR equal. mCp is a constant, so you can get them out. mCp change in temperature versus time. That's what we got. That's what we get. Now check this out. What happened with this is kind of let me fix this. It's kind of ugly. mCp, there we go. NCP T1 minus NCP T reference, but I have here, let's see, minus, this is positive. I'm gonna check the sign. This time this negative, minus this negative, positive. Now these cancel out with this one, they are the same. After you cancel that out, you can combine this term and this term, so you end up with N1CP parentheses, that's a common factor, T1 minus T2 plus QR equal MCP dt dt. Temperature, the rate of change of temperature versus time here. Now let's divide by MCP and let's get this in this way, make life easier. We end up with N1CP over MCP T1 minus T2 plus QR MCP. You see, that's the differential equation for how the temperature change within this vessel with inlet and outlet and a resistant. Alright, so now let's simplify a little bit. CP cancel out and you end up with the change in temperature, the rate of change of temperature equal M1, the flow of mass, divided by M, T1 minus T2 plus QR over MCP. So this is actually the differential equation for a vessel. Let me put a vessel here that looks like this. Adiabatic, no heat exchange with the environment, an inlet, an outlet, and a resistant heating the material inside. That's the QR. How we do this now? How we work with this equation? Well, this equation, you can work for three parts, like we did on our fed batch reactor. There's always three parts to this. Like for example, there's a part that we call steady state. Steady state. That's part one. Part two we call dynamics, as always. And the third part, process control. In process control, we establish a set point. We want that the vessel reach some set point. In dynamic, we just let it go. Remember that in dynamics, most cases, this is Kc, the constant, the proportionality constant equals 0, because you are running the system in manual. The system is in manual. Now here you establish the set point and the system should drive the temperature to your set point. So these are the three things that we typically do with this type of differential equation. Now let's start with the steady state. In most cases, in the steady state, for the steady state, what's going to happen is that dt, I'm running here dt, but actually let me fix this. Where's the problem? Right here. I put T here. It should be T2 because that's the temperature. I want to be sure that you correct this. This is T2. There's always, in all of them, in the differential equation, is the temperature inside the vessel. Let me fix it. Fix it. Fix it. Fix it. Here we go. This is the differential equation, how the temperatures change inside the vessel, but that's T2, which is actually the exit temperature here. That makes sense now. Now, that means that for a steady state that I'm studying, dt2 dt, I'm saying that is 0. It's very important that we understand that. Now, if it's 0, we end up with M1 over M T1 minus T2 plus QR over MCP, obviously equals 0. Then what we're gonna do is, most of the cases, is try to get what is T2 from this equation. Basically, notice that the M, if you multiply the whole thing by M, it cancel out. M by 0 is 0, so you end up with this equation, say M1 T1 minus T2 plus QR over CP equals 0. So the M disappear, and then let's put the M here as well. 0 by m, that will be 0. Now, as I said, in most cases we want to know what is T2. If I work this out in detail, N1 T1 minus N1 T2 plus QR Cp equals 0. So we want to have the equation in terms of this. So if I go and take this way, so it's going to be N1 T1 plus QR Cp equal N1 T2. If I divide by N1 everybody, so it end up like T2 equal T1 plus QR over the flow of mass into the vessel times the constant Cp, the Cp constant. This is the steady state equation. It's very important that we understand that this steady state equation does not m. I don't care about the m. It could be a big vessel, could be a small vessel, but the steady state will not care about the amount of mass you have in the tank. However, for the dynamic, oh yes, it make a big difference. How long it takes a vessel to arrive to a certain temperature. If it's too big, it's going to take a lot of time. If it's small, then it's going to be faster. So that's for the dynamics. But for the final value of steady state, they will be equal. I mean, if all parameters are the same, it will gonna be equal. It doesn't matter if the mass is big or small. They're gonna reach the same temperature. All right. So we got the steady state. What we're gonna do with that steady state? Well, let's get a system that is auto-regulating. Let's put it here. A system. Let's say a system auto. I'm gonna write it like this: auto-regulate. If a system auto-regulate, it means that it can have steady state, and that's what I prove here. A system that auto-regulate, it has a steady state. That a steady state is shown here. T2 equal T1 plus QR over m dot Cp. Let's call this M1. So to make a story short, if I know QR, if I know the mass getting into the tank, the mass flow, I can get what's going to be T2, because T1 is a known value. I mean, what I'm saying that if in this equation you have 5 variables, if I know 4 of them, in most cases will be this one, this one, this one, and this one. So it's going to be QR, N1, T1, and Cp. That is 4.18 kilograms C, degrees C. T1, let's say that is 25. QR depend on what adjusting you did to here. You see? Because I have a maximum. What adjusting you will be doing in the VBR. Somehow here I'm missing the VBR. I don't know what happened to it. Let me put it down back. Let me write it down. Somehow got deleted. There we go. This is the VBR. So you adjust it to 0, so the amount of heat generated by this guy will be 0, but if you adjust it to 100%, that will be 5 kilowatts. All right, so let's get back here and let's do some example here. For example, let's say that QR is going to be adjusted to 50%, so the maximum is 5 times 50% divided by 100, so that's going to be 2.5 kilowatts. All right, so what about the M1, the flow of material? That flow of material will be the maximum, which is 0.126 multiplied by the adjustment. Let's say that we're going to adjust that flow here at the top of the reactor here, of the vessel, at 30%. So N1 will be adjusted at 30%, meaning that this valve will be adjusted at 30%. That's what that means. All right, so if we do that, 0.126 times 30% divided by 100, that would be equal 0.037. So after that, then I have everything that I need. then T2 for this particular case then will be T1, which is 25 degrees, plus now QR was adjusted at 50%, so that's 2.5 divided by m dot, that's 0.037a, also by the CP, that's 4.18. So the result finally here is 40.82 degrees C. So that's the temperature you will reach if you set these parameters the way they are here. Eventually, this is the final temperature. You're gonna reach that temperature, meaning that if you are starting a dynamic, and here we go, let's say that we are starting a dynamic temperature here, and we have an initial, our initial vessel is at 25 degrees, and you at time 0 you start to adjust like QR to 2.5 and the flow of mass in 0.037a, this system eventually will reach that's the 40.82. You see? Now, if you for any reason want to understand what would be a nice set point to set to this system, well, you have to find the maximum and the minimum. Let's work that out here. Like for example, QR is the variable that you are trying to manipulate that variable. You see the TIC is going to the VBR, so you are adjusting QR. Not sure what happened here, but I'm missing something. See if I can fix it. QR, you are adjusting the amount of heat, and this is a sensor for TIC, a controller, and a set point, and you are going right here to the VBR. Meaning that if you adjust COR, you are adjusting how much heat you want into this vessel. With that said, let's go back here and let's work out a couple of things. Like for example, so we know that the temperature, the steady state temperature T2SS is equal 40.82, and that happened when QR is equal 2.5 kilowatt, meaning that the COR was adjusted at 50%. Now the question is, what's going to be T2SS when you do the adjustment of, let's right here QR for a second, and let's say COR equal 100%. If you adjust that to 100%, QR will be to the maximum, and that's 5 kilowatts. On the other hand, you can also get another temperature SS at when you adjust QR, and let's say that the COR will be adjusted to 0%, that means QR will be 0. Now if you check the equation, let's write the equation here for a steady state, no matter what, T1 plus QR over m dot Cp, and this one is the same, T1 plus, sorry for this, T2SS plus QR over m, sorry, this m is not this one, is m dot Cp. So here's the story. QR is changing. Like for example, this will be straightforward because QR is 0. It means that eventually T2S at COR 0% will stay the same, so there's not going to be any increase in temperature. T2SS will be T1, whatever is the temperature getting into the vessel, which is about 25 degrees. So basically you can say that this equation here, T2SS minimum, is T1, which is equal to 25 degrees C. What would be the maximum? Now for the maximum, we gotta go do some number here. Let me get this a little bit better. So here T2SS equal 25 plus QR, which in this case is 5 kilowatt, divided by the mass flow, but that mass flow will never change from 0.037a 4.18, and that will be 56.64. So there we go. So you get let me organize this. So basically you have a T2 SS equal, in this case is about 40.82, but this is at COR equal 50%, but you also got a T2 maximum equal 56.64 at COR equal 100%, and you got a T2 mean or T2 SS. Let's always put the word SS, meaning steady state mean, minimum of 25 degrees C at COR equal 0%. So now we have clearly established that this system has, first of all, a steady state value, but it can also have maximum and minimum. With that said, now the set point can be easily established, because the set point for this system has to be under these parameters that we are talking, has to be a value between 25 and 56. Whatever you set as a set point, that will work okay. Meaning, like for example, if I say 50 degrees C, so the system will look like this. Let's do a graph, and this is what I'm saying. Like for example, at time 0 you have an initial condition at 25 degrees C, and you hit the content until reaching a steady state value of about 40.82. Here you want to change the set point, and the set point for this case is going to increase, let's say, to 50. So that the system, what the system will do is, if this is the, let's write here the other part of this, which is called the CO R, from zero that it was, it jumped to here, and that's 50%. Now at 50%, you leave it there, don't move it. But now, since you are going to change the set point, as you change the set point, the system, this got increased. I mean, this COR has to increase to drive to the new temperature. So this will increase to whatever value, let's put it like this, and eventually the temperature will go to a higher value, and that should be the 50 that we are looking. But actually the process by itself is actually starting here. So here is where you start with a 0 back again. So because this part here was more like dynamics, so here this part was more like dynamics, and it's here when you introduce the set point, because that 50 is a set point, then we have here process control. One thing is dynamic and another is process control. So let's see where we are now. So we have a set point. I think that we are ready to do process control. We're going to do process control into this system. And how to do process control? To do process control, let me recover back where we were. So we're going to do process control. To do process control in this tank, we have a tank. We know that the tank is adiabatic. This is exit temperature, which means that the vessel is at T2. This is T1. T1 getting through here with a flow of N1. Inside the vessel, there's a big mass. It's a mass of material there. And we have a resistant producing heat here, it's a heating element, heating everything here, and that has a VVR. This is connected to the wall, and you have here, let's put here a TI, a TIC, and from here, that's the CO that will graduate this to get whatever heat you have here. So now you have a set point. Going back to the PNID, I want to be sure that you understand the PNID. So in this case, I either can control VVR or the valve. I decide to control the VVR. So meaning that is the heat QR that eventually will this actuator will work on the QR. Now, so we want to do process control. To do process control or a simulation of process control, I need three equations. The first equation is the equation for the system. The equation for the system is, we derived that already, dt2 equal m1 over big M t1 minus t2 plus qr over m Cp. So that's the equation, the differential equation that describes how the temperature inside this vessel will change. The second equation that I need is the variable that I'm going to be manipulating to reach whatever temperature I want. In this case, it's QR. So QR is going to be QR max, whatever value, which is about 5 kilowatt, times the COR, which is what coming from the TIC, is the signal from 0 to 100, and that divided by 100. And the third equation is the controller equation. That's right here, the controller. What type of controller we're going to be using? What is the controller equation? Now, in controller equation, we have worked a lot on what we call a proportional controller. The equation will look like this, that COR equals COR bias plus KC have a sign, right? Is either negative or positive, depending whether the system is direct acting or reverse acting, times set point minus PV. Another way to write that down is that COR equals COR bias plus KC, which is the proportionality constant time the error. That's a proportional controller. Now we're going to introduce a different controller. We're going to introduce something that is called a PI controller. A PI has two terms. Let's work that out. The COR will be COR bias, no problem there, plus KC times the error. This is the part, the proportional part. How about the integral part, the PI? PI is proportional integral. So the integral will look like this. Kc over a variable that we call tau e, which is the constant for the integral part. And as the name implies, integral, there's an integral, but of the error dt from 0 to whatever time we are. So we end up having a kind of a larger equation. You know, this is proportional, but this is a proportional integral. And this part here, Kc over tau e, is a constant, but now we have this part here, which is the integral part. So what we are saying is that this part here is the proportional part, and all this is the value for the integral part. So that's what we call a PI. And this type of controller, this PI controller, is better for systems that do the following: that they auto regulate, system that behave nicely, in other words. So in other words, you have a good steady state value like shown here. A system that will do that is nice to, you can use a PI controller and will do wonderful, it will work wonderful on it. Now, a system that do not auto regulate, you are better stay off PI. You better use a proportional controller. Better use a proportional controller for systems that do not behave properly, like they don't have a steady state. Like a very good sample for that is when you have a vessel like this, for example, only a pump getting material out. That system is and you want to control the, for example, you want to control the level, and you have an LI and an LIC, and this is going to the VFD of the pump like this, and you have a set point here. This system is not good for a PI controller. You are better with a proportional controller on here. It's better with a proportional because this system does not does not auto-regulate, so better use proportional. If the system has good steady state for at least 3 steady state based on the variable that you are manipulating, then definitely a PI will work okay. And that's what I'm saying. Now, how we apply this equation? First of all, let's understand this integral part. What that integral part means. The integral part is of the error dt from 0 to t is actually, we call this the area under the curve. The area under the curve. How that, how you work with that? Oh, very simple. This is what I'm saying. You have the error here and you have time here. At time 0, you always have an error, like set point minus PB always produce an error, right? So you have a number here. For the timing, let's say that that's 5. And 10 seconds later, because that's our delta t, 10 seconds later, that error increases, let's say, to 10. So we are here. Now, 10 seconds later, that's 20. And let's do this 20, 30, up to 40. And there it dropped from here to 0. So let's start to draw the curve. So we have a curve like this. 1 point here, 1 point here, and 1 point here. Now from here to here, let's say that it dropped to minus, because it can go to the negative, to minus 5. So pretty much somewhere here. All right. And from here, it went to 0. So there we go. So you have basically if I ask for the area under the curve, what I'm asking is for this. These are the points where the changes are happening. So the area will be this, and this. So 1, 2, 1, 2, 3, 4. How can we calculate the area? Area 1 is going to be this area here. So if I said that this point here is going to be 10, I don't know what happened, that's going to be 10. So we have 5 plus 10 divided by 2 by this distance here, which is 10. All right, so how about area 2? Area 2 will be this 10 is the average height, 10 plus 0 divided by 2 times 10. Area 3, that will be this area now from 0 plus negative minus 5 divided by 2 multiplied by 10. And the last area, area 4, equal, here we go from minus 5 plus 0 divided by 2 multiplied by 10. 10 is the distance. So when you're talking about area, you see, this is the area that I'm interested here, and so in here, and so in here, and here. So let's say, let's work this out. That would be 15, 7.5, 75. How about this? 10, that's 5, that's 50. That's 2.5 negative times 10, that's 25. And this is going to be 2.5 negative times 10 is so this will be minus 5 plus 0, that's minus 5 divided by 2, that's negative 2.5, the same as this one, but don't forget the sign here, that's negative, and so here as well, that's negative 25. So if I'm asking the area under the curve from 0 to 40 seconds, that would be the sum of each area from I equal 1, in this case, to 4, because I divided the whole thing in 4 sections. So meaning that what I'm going to have is, for example, minus 25 minus 25, that's going to be that's negative 50. With this 50 is gone, so we end up, the total area here under the curve is 75. 75 has unit. The unit that it will have is the unit of the error. The unit of the error is, if you remember, what the unit of the error, that would be set point minus PB. Set point minus PB, that's the unit of centigrade. But it also will have unit of time, of second. It's kind of weird, right? Because you end up having these two unit. Let's write this second better so that don't confuse nobody. Times second. All right, so that 75 has that type of unit, degrees centigrade second. Now, remember, in my controller, that area is multiplied by two factors, Kc over tau I. Now, Kc, we already know Kc has unit. What is the unit of Kc? The unit of Kc is percentage over degree C. Tau I must have units as well. Those are seconds. So if you take those units, like for example, that's 75 that have degree C, fix this, 75 degrees this is second. Now Kc, the unit of Kc, whatever is this number, is going to be percentage over degree C. Now what's going to happen is you have that Kc, but you also have 1, let me put it here, 1 over tau I has unit as well, which are seconds. So second cancel out with second, degree C cancel out with degree C, and eventually you got 75, which is just the area under the curve, times Kc over tau I, which is just a number, but at the end is percentage. And that makes sense because the CO, the controller output here, where's the controller output? A little bit more. This controller output is measured in percentage. All right, so that is basically how that works. Now, let's make an example here. Let's say that I want to control, and as always, when we are talking about controlling something, we are talking about a table, a process control table. That's time, the error. Typically after the error, watch out for this, the area of the segment. The area of the segment is this calculation. So after that, then we have the sum. The sum is this part here, in where after you calculate each one individually, then you start to add them up. So you have this sum here, and eventually after you have the sum, the next thing that you want to have is the calculation of the actual CO calculation, and then any corrected. So you need to correct the CO for whatever reason, you know, above 100 you put 100, if it's below 0 you put 0, and after that then you put like for example here is the QR, because that's the variable that you are manipulating, and finally the temperature, which as I was saying before, since we are starting this process from a steady state value, since we are doing that, remember that state value is coming from above right here. A little bit more. We are starting actually from here. That's where we're starting, meaning that 40.82. So we go back here to my table, and here is the important part, 40.82. And that's at time equals 0. So what's going to be the set point? We're going to do one line here, only one line, because then we're going to do this in Excel, and so it's easier in Excel. So what's going to be is that the set point, as I was saying on this process, let's put those parameters somewhere here so that we don't get confused. Okay, let me put it here. Set point for this is 50. Set point is 50. So what's the error? the error will be the difference between the set point that I want and where I am right now. I am in 40.82. That's 9.18. The area of the segment. This is the first error. If this is the first error, you are right here. You are here. There's no area because you are right here. It's just a vertical line. There's no area. You haven't advanced yet in time. So that means that this is 0. What is the sum? The sum is something that you sum this, and the other, and so this is 0 here. Now, what is the CO value that you want to calculate here? Well, that CO will depend, and let me write here. Let's say that Kc is positive 10, and the tau I is positive. Obviously, this is time in seconds, so it must be a positive number, 500 seconds. All right. So, with that said, then CO equal. Now, how about the bias? Well, you reached this 40.82 because you set the bias to 50%. And that's a very important thing that you have to consider here on the second part. So we start with a 50%. That's where it was. Let me write it like this only, 50. Just a number. Plus Kc, which is 10, times the error, which is 9.8, plus Kc over tau I multiplied by the sum. But in this case, the sum is 0 because I'm in the first line. So eventually, what I'm doing is, in essence, so that would be 50 plus, so that would be 50 plus 91.8, so that's 141.8%. So we write that here, 141.8. That number is above 100, so definitely this is 100, meaning that QR will go to the maximum. Remember, QR in any time equal QR max. That's the resistance value, QR max times COR divided by 100, which is in this case QR max is 5 kilowatt multiplied by COR, which in this case is 100 divided by 100. So definitely, finally QR will be 5 kilowatt, which is the number that will go here. So it means that since we are trying to increase the temperature to a set point of 50, but we are at 40.82, the system is just increasing the value of the watts that we are supplying to the vessel to the maximum of 5. But that's just the first line. There's nothing else to do. What's going to be the second line? The second line is, as soon as you increase the time to 10, you got to calculate what's the new temperature here. That new temperature is based on the model. If you remember the model, the differential equation for this system was like this. The change temperature T2 equal m dot over m T1 minus T2 plus QR over mCp. So that's the equation that you have. Now, that equation has to be on the integral form, and we use Euler for that. In the Euler version, that equation will be like this: T2 at time t plus delta t equal T2 time t plus delta t parenthesis m dot over m T1 minus T2 plus QR over mCp. Close this. Now, this T1 is a constant, but this T2 is the one changing, and that T2 is evaluated also at the same T here. All right, so let me write this better so that doesn't look that bad. So this is T1 minus T2T parenthesis plus QR over mCp. Now, that's the Euler version, and that's the one that I'm asking here. So that means that our new T2 T plus delta T, or T2 at 10 seconds, whatever you want to, you want to write it like that, is equal to the original, that's 40.82 plus 10. What is M1? But M1, you remember, that's another parameter I'm going to write here, was 0.0378, based on the fact that CO1 was adjusted to 30% and that the M maximum was 0.126 kilograms per second. So that's where you get this M1. So that will be 0.037A, and now I have an M. I need an M value. The M value is the mass of this tank. Now this tank, let me redraw it here. Let's say that the volume on this tank is 30 gallons of water. If you convert that based on the fact that the density of water is 1 kilograms per liter, then that volume will be converted, or that 30 gallons will be converted to a mass inside the vessel of 113.55 approximately kilograms. With that number is the one that will go here. 113.55 kilograms. T1, that's 25, minus T2, this is in the table, that's this 40.82, plus QR, which is in this case is 5, divided by 0 by the M. Sorry, this is not M dot here, it's M, big M, that's 113.55, and 4.18, close the parenthesis. So we have this parenthesis and this parenthesis. Now we need to do all that math with a nice calculator, and let's see what end up being. T2 equal 40.82 plus 10 times, this is going to be negative 5.28 times 10 to the minus 3 plus, and let's work out this number here, and that's going to be positive 10.534 times 10 to the minus 3. Final result 40.87 degrees C. So it just increased a little bit. I mean, that's about 10 seconds. So that's why doing this by hand is a little bit tedious, because when you get this 40.87, then you got to go back to this table and do the correction on the error. That will be, remember the set point will not change, it's still 50, so that will be 50 minus then the 40.87, that's 9.13. But here's the story. Now area of segment is not going to be 0 here, because that basically will be the sum of these two guys. So let me work that out here. So this is getting a little bit crowded, but let's work that new area of segment here. So that would be, let's do it here. So that would be 9.18 plus 9.13, all that divided by 2 multiplied by 10, and that's area of segment 1, and it start here. So with that said, then let's work out this number. That's gonna be 91.55. So that's the number that goes here, 91.55, which happen to be, you sum these and these, that would be here 91.55. Now that number will have some impact on this CO calculator, and the CO calculator for that case will be, let's write it here, will be this is COR. The bias is 50% plus KC, which is 10, positive 10, times the error at that point. The error in the table is 9.13. Careful now. Plus KC, which is 10, I think tau E, I always call this tau E, but actually it's tau I. Sorry for that. It's called tau I. Sorry, tau I. Because tau E will be like this. Tau E. It's called tau I. Tau I will be 500, and that multiply by the sum at that point. The sum at that point is just, I'll go back to the table. I know what it is, but just to show you, always keep looking the table. It's going to be 9155. So we put here 9155, and the final result for this will be, okay, for 143 times 131 percentage. So that number is the one that goes here, 143.113. Let's write it like this. Whatever, this is above 100, so you write here 100, and QR will stay at maximum energy flow. In this case, the heating element is producing as much heat as required to try to increase this temperature. The next thing that you will do is, again, you want to recalculate back again the new temperature, this one here, because the temperature increased a little bit, and that's how this will go. You can do like 3 calculations by hand, but after the 3rd calculation, doing this by hand is just crazy. I would not do that. More than 3 calculations, no, that's good enough. So 0, 10, and 20 maybe at the most by hand. So you know what you're doing. That you can convert. The idea is eventually that you can convert this process control table to an Excel table, so that eventually you can get a nice curve and the CO here, and like for example, you were here at a given temperature, initial temperature 40.82. You want to know how the system eventually hit what you want, which is the 50, because that's my new set point. And you want to know what the CO did. The CO originally was here at 50, so the CO probably increase it as well, and that's the COR. So you want to know these 2 curves, and that's for process. Again, this is what we call process control. Okay, because we have the COR and the PV, in this case the PV, which is temperature. So what we're going to do now is do the same, all this calculation, but within Excel. I don't want to do this by hand anymore. So the 20 will be okay. I can do that by hand, but the other stuff, no, because we want to do these, and that might take a while to carry this on. Let's work on Excel now. That will be kind of a part 2, which is called for process control. We did steady state. We know that the system auto-regulate, and that's what we are sure that yes, we can use a PI controller on this system because it's auto-regulate. If the system does not auto-regulate, don't try a PI, try a proportional controller. So for now, we move to Excel. Wait for that.